This is section 6.7, and we're now going to move to talking about mass, moment, and center of mass. I should actually warn you there's a lot of material in section 6.7. We're going to kind of split it into three separate parts, starting with this mass, moment, and center of mass. Now, in general, when we think about mass, we usually think about three-dimensional objects having mass. Our density is the concentration of mass in an object. So if we've got some three-dimensional object with a particular volume, then if the density is constant, the density would simply be that total mass divided by the volume of the object. Or we might write mass m divided by volume v. Right? Solving for the mass, then mass would be density, rho, times volume, v. This symbol of density, right, by the way, is the Greek letter rho, R-H-O. All right, if we really are in a three-dimensional world, mass units might be something like kilograms or grams, volume might be cubic centimeters or cubic meters or something like that. That would be the ideal situation. Unfortunately, we're going to have to wait until Calc 3 to go any further with this because we can't handle a three-dimensional world mathematically quite yet. In this section, we're going to be doing the same idea, but we're going to be dealing with density of objects that are essentially linear. Think thin wire or thin bar, in fact, infinitesimally thin, so that we can think of it as just having length. The width is essentially negligible. As I said, we're only equipped at this point to handle that one-dimensionality mathematically. In this case, instead of thinking of our mass as distributed over a three-dimensional volume, we'll think of our mass as being distributed over this one-dimensional length. So, for example, density would be the total mass of the object divided by its length, right? The analog of the three-dimensional case, or m divided by L. And again, just a little bit of algebra. To solve for the mass, we'd have density times length. This case, we can go on and generalize a bit. So let's see where we're going with this. We now are going to turn to the question of what happens if the density is not constant. What if density varies along the length of this thin bar? So our density, rho, is actually a density function, rho of x. And that function gives the density at the bar at some point x units from the end. So we're essentially defining the end of the bar here to be x equals 0. And at any particular point along the bar, if I took that x value and plugged it into the density function, it would tell me how dense the bar is at that particular point. That allows us to deal with bars that are more dense in areas than they are in other areas. Okay. Let's call this end of the bar x equals L. And I'm going to imagine for a moment just one small section of the bar. So if I had one little piece of the bar here, the length of the bar, or that little piece of the bar, I could consider to be a little piece of x. So I'm going to call it delta x. And I'm going to say if I make that piece small enough, even if my density is variable, I can consider the density to be constant just on that little tiny piece. It wouldn't vary very much if I make the piece small enough. So rho here, or rho of x, constant on this small section. If I do that, then I can say that my mass is the density times the length. Oops. Mass, density times length, or rho of x times the length delta x. If I then took a whole bunch of those little pieces and I added up all of those masses, I would get an approximation for the mass of the whole thing. I would say that mass then is approximately the sum of all of these little masses, rho of x, delta x. And since I'm going to change the location of my x, I'm going to call it xi. So I'd have one x here and another one there and another one there and so on. And I could do this for n separate masses, splitting this up into n pieces. We've seen this before, right? If I let the size of my pieces go down towards infinitesimally small, close to 0, and I let the number of pieces approach infinity, then I can get an exact value for the mass of the entire bar. Technically, it would be equal to the limit as I let the number of pieces go to infinity. But we know, because we've seen this so many times, that that's just the definite integral of rho of x dx. And we'd be integrating from x equals 0 to x equals L, the length of the bar. So with a variable density function, we'll find the mass by integrating that variable density function over the length of our object. And that's actually written out there formally for you at the top of the next page. All right, so let's try this. In example 2, suppose that our bar is 3 meters long, and the density of the rod in kilograms per meter is rho of x equals 2 plus x. Let's just think about the situation for a moment. Where is this rod lightest, and where is it heaviest? Well, let's see. The density at x equals 0 would be 2 plus 0, or 2 kilograms per meter. And the density on this end, rho of 3, would be 2 plus 3, or 5 kilograms per meter. So it seems as though this is going to be the lightest, the least dense over on the left side, and the heaviest or most dense over on the right side. Lightest on the left, heaviest on the right. All right, what's the density at the exact middle of the bar? Well, let's see. If it's 3 meters long, then the exact middle of the bar here would be x equals 1.5. And so if I found the density at an x value of 1.5, that would be 3.5 kilograms per meter. All right, I'd now like to find the mass of the entire bar. And I can't just algebraically take the length 3 times the density, because the density is different at different locations. Instead, we're going to use this integration mass formula. And we're going to say we want to integrate over the length of the bar, 0 to 3, our density function, 2 plus x dx. And that's not a very difficult integral to do. Let's just write that out. 2x plus a half x squared, evaluated from 0 to 3, would be 6 plus half of 9 minus, when you plug in 0, everything is 0. And that's going to give me 10 and a half. This would be mass, so it would be kilograms. So that whole bar would have a mass of 10.5 kilograms. All right, part D, we want to find the mass of the first half-meter section and the last half-meter section. So basically I want to know if this is x equals 0.5, half a meter, what's the mass of that little piece? And then if I go in a half a meter from this end, what's the mass of that little piece? So half a meter here would be an x of 2.5. So the first half meter, I'm going from 0 to 0.5. Integrating again my density function. And I won't write out all of the details here, just the arithmetic, not difficult to do, but plugging that in, I got 1.125 kilograms. And then the last half meter section, now remember, it's heavier on the right end, so we should be getting a larger mass for that last half meter than we did for the first. We're now integrating from 2.5 to 3. Still the same density function. And again, just routine running the integral. I actually got 2.375 for that one. So as predicted, the right-hand side certainly heavier than the left-hand side. All right, so that's mass. We just integrate our density functions. Second concept here is the idea of moment. In physics, a moment, sometimes called the first moment, is the product of any physical quantity times its distance from a fixed point. We're going to be discussing moment of force, where force is represented by the weight, and actually in our case we're even going to go with mass of the object. Since we're staying on Earth, mass and weight have an exact close relationship, so we won't worry too much about that at this point. All right, let's imagine the fixed point as the end of a lever here embedded in a wall. So this is kind of like a board stuck in concrete or something like that. And if you apply this mass M at the end of the board, right, if your board's flexible enough, it's going to bend it a little bit. And the moment is defined as the mass times the distance from the fulcrum. So the mass M times the distance from this fixed point, x. Mass times distance. The moment actually measures the tendency of this object to rotate around the fixed point. We might see that as the bend in a board, or as we'll see down here a little later, if it's more of a seesaw situation, you could see it as the tendency to tip around the fulcrum. When you think about the two quantities involved in the calculation, you can see that to increase the moment, we can either make M bigger or we can make X bigger, right? We could either use a heavier weight, more mass, or we could put it further out from the fixed point. So we can either increase the mass or we can increase the distance. And of course, to decrease exactly the other opposite. We could either use a lighter object so we can decrease the mass, or we could decrease the distance. Or both. Okay, let's go on a little bit more with our ideas of moment here. Here I was thinking of a lever as being like embedded in a wall. Another way of thinking of our fixed point is like the fulcrum, kind of like the old-fashioned seesaws, right? Teeter-totters. If I imagine the fixed point as the fulcrum of a lever, the fulcrum being the balance point here, then we still want to define x equals 0 as the end over here. And I'm going to say, let's imagine that this point C, or x equals C, is the point where the fulcrum supports our board. May or may not be right in the middle. And then, of course, this over here, x equals L, would be the length of our board. If we, once again, start at x equals 0, our fulcrum is at this point x equals a constant, and now we apply a mass at some particular distance from the fixed point, then the distance here from the mass to the fixed point is actually going to be x minus c. Right? This whole distance x minus c gives me just this little piece here, just this distance from the fulcrum to the mass would be x minus c. And of course, when you place that mass on there, it's going to have that tendency to rotate about our fulcrum, which we call the moment. Our mass then, or excuse me, our moment, capital M, is still going to be mass times distance. So our mass, if we call that M again, and our distance this time is going to be x minus c, where again c is the location of that fixed point or that fulcrum. Moment still measures tendency to rotate. In this case, about the fulcrum. And to increase the moment, we can either increase the mass or increase the distance from the fulcrum. To decrease moment, we can either decrease the mass or decrease the distance from the fulcrum. All right, we will get into some examples of moments in just a second. Before that, there's a little hint in the picture at the bottom of your page here, but think about where we might use the principles of moments in everyday life. If you think about it, here's this guy trying to pry loose this big rock, right? What are the two things that you can do to move a heavy object with some kind of a lever? Well, you can either increase the mass, or the counter mass really would be your own mass that you're pushing with, which you may or may not be able to do if you're pushing with all your strength. Or, and this is what we usually do, we increase the distance, right? If you can't move it, what do? You get a longer lever. Same concept when you're trying to loosen a screw or something, right? If it's stubborn, you need a longer pry bar, you need a longer screwdriver, you need a longer lever, longer wrench, that kind of thing. So we actually use this concept of moment in everyday life quite a bit. All right, let's look at some actual examples of calculating moments. I'm going to stick with the idea of the board. Sorry about that. I'm not going to do a moment yet. Concept of the board fulcrum system. We're going to concentrate on that just a little bit. And I want to do one other thing before we actually do any calculations. Let's suppose that instead of having just a single mass set on this board, we actually have multiple masses applied at different positions along the board. What is the resulting moment going to look like? Well, if I have multiple masses, I would just add up the various moments. Okay? So, here's my x equals 0. Here's my fulcrum at x equals c. And let's suppose that I've got this little mass here. I'm going to call it M1. And it's sitting at an x value, x equals x1. Then let's suppose I have another mass over here. We'll call that one M2. And it's sitting at a position, x equals x2. Then the total moment is just going to be the sum of the moments of the two separate masses. So for this one, I would have my mass M1 times my distance, x1 minus c. And for this one, I would have my mass M2 times my distance, x2 minus c. Now notice what's going to happen here. Here, x1 minus c is going to be a negative value. So this is going to give you a negative contribution to the moment. Whereas over here, this x2 minus c is going to give you a positive value. So here you're going to get a positive contribution to the moment. If the overall moment turns out negative, this is going to tilt to the left. And if the overall moment turns out positive, this is going to tilt to the right. And it's just going to depend, of course, on the actual values of the m's and the x's. All right, let's try one of these out. I'm going to go ahead and create a system here for us. Let's say this is x equals 0. And I'm going to say that my first mass here, and these are going to be in grams, so this is going to be 5 grams. I'm just going to put down the 5, but it's 5 grams. And let's say this distance is at 3 centimeters. Let's say I've got another mass over here closer to the fulcrum, and this one's going to be 9 grams. And let's say that's at 8 centimeters. I'm going to put my fulcrum here at 10 centimeters. I'm going to put another 6 gram mass over here at 13 centimeters. And then finally I'm going to put a 7 gram mass over here at 18 centimeters. These are all grams. Maybe I'll try and sneak the G in. There we go. All right, so for my overall moment, for each one of these, I'm just going to multiply mass times distance from the fulcrum. So for my first one, I'd have a mass of 5 times 3 minus 10. Notice that that is going to turn out to be a negative directed distance. So that one's causing it to tilt to the left. Plus here I've got a mass of 9. My directed distance, 8 minus 10. Again, a negative contribution to the moment. A mass of 6 times 13 minus 10. That one's going to have a positive contribution to the moment. And then finally the mass of 7 times 18 minus 10, another positive contribution. And then it's just a matter, of course, of doing all the arithmetic. And if you do that, you get 21. Notice in each case, the mass is in grams, right? And these are in centimeters. So the units of this answer are actually grams times centimeters, or grams centimeters. It's a positive moment, so we do know that this board would tilt to the right. All right, let's generalize this a little bit now. Let's suppose for a moment that instead of placing individual masses on the board itself actually provides the masses. That is, each little section of board has a mass of its own, and each tiny section then contributes and constitutes its own mass. Here's my x equals 0. Here's my fulcrum at x equals c. And the other board we'll call the length L. I'm now going to say, let's imagine a tiny little section of board in here. The length of that little section I'm going to call delta x. And we'll imagine that it's at some random point x. The moment of that little piece would be the mass times the distance and if I further say, what if the mass is determined by the fact that we've got some variable density function? Let's suppose this board has density function rho of x, then the mass is the density times the length. Rho of x times delta x. And the distance from the fulcrum, is x minus c. Now, this is just one tiny piece, right? So I could say this is the I moment, and that would be rho of xi and xi minus c. And I could say there are a whole bunch of those. So the total moment could be approximated by summing up all of the moments of the individual tiny pieces. And I'm just going to call that rho of xi times xi minus c times delta x. And we could do that for n separate pieces. All right, you know the drill. We've seen this a lot. If I want an exact value for the moment, I would have to take the limit as the number of pieces go to infinity, and each individual piece shrinks down infinitesimally small. And that is the definition of our definite integral. Shrinking my delta x infinitesimally small so it becomes a dx, and integrating over the whole length of the board from 0 to L. And that becomes the moment of the entire board. All right, that, and actually I'm going to have to ask you to fix this a little bit. There is an error. I accidentally left the minus c out of this equation, so let's go ahead and fix what's at the top of the next page. The total moment for a thin bar with density function rho of x supported on a fulcrum at x equal c, should be a c, is the integral, and I'm just going to rewrite this, from a to b, if a and b are the endpoints of the bar, of rho of x times x minus c dx. All right, so here we go. Here's our example. A thin bar of length 10 centimeters is supported at its midpoint by a fulcrum. Suppose the mass of the bar, find the mass of the bar at the moment and the moment, I can't read. Find the mass of the bar and the moment of the system under these various conditions. All right, so we've got a bar of length 10. It's supported at the midpoint, so my fulcrum here is at x equal 5. And I want mass and moment, first of all, for a density function of 8 grams per centimeter. All right, mass is the integral of density dx. So that would just go from 0 to 10. The density is 8 dx. Integral would become 8x from 0 to 10. And 8 times 10 is 80, minus 0 is still 80. And the mass of this full board, or bar, is 80 grams. The moment is the integral of the density times x minus c dx. So in this case, 0 to 10. And again, our density is 8 times x minus my c here is 5. That's where my fulcrum is, dx. And again, I'm going to leave it to you just to do these integrals or use technology to do them. They're simple integrals. This one comes out to 0. And this is a moment, so it'll be grams centimeters. And hopefully, if you think about that one, it makes sense, right? Since this is a uniformly dense bar, and we've put the fulcrum right in the middle, it shouldn't tilt either left or right. It should be perfectly balanced, meaning the moment is 0. All right, let's try a couple of others. For B, my density function is x plus 9. So my mass, I won't rewrite the formulas, but density dx would be x plus 9 dx, integrated over the whole bar from 0 to 10. And that turns out to be 140 grams. The moment, density times x minus c. X plus 9 is my density. X minus the position of my fulcrum, which is 5. And again, just integrate that either by multiplying it out and integrating by hand or by calculator. And I got 250 over 3 grams centimeters, or about, what is that? It's about 83.3. Notice I got a positive moment this time, which hopefully makes sense. Since the density function was x plus 9, over here the density is just 9, but over here it's 19. It's heavier on the right-hand side, so it is going to tilt toward the positive side, the right-hand side. All right, one more. C, my mass, integral 0 to 10 of the density function, 1 plus x squared. Oh, you know what? I actually wanted to change that one because I had a point I wanted to make here. Do me a favor and fix this one. Let's use a different density function. I want to use 150 minus x squared instead. When you integrate that density function from 0 to 10, you end up with 1166.67. And that would be grams for the mass. And the moment, we take that same density function, 150 minus x squared, times x minus the position of our fulcrum of 5. And this one came out to negative 833.33 grams centimeters. So notice with a negative moment, this one's going to tilt to the left. And again, if you think about this density function, on the left-hand side at 0, we'd have a density of 150. But on the right-hand side at 10, 150 minus 100 would be 50. So it's heavier on the left end, giving us that negative moment. Right, let's see where we're at here. All right, let's go on to part C here, center of mass. And sorry, I had a little bit of a recording snafu, so I've written out a little bit of this, but we'll kind of talk through it before we go on to the next example that I haven't done already. We're going to be talking now about the idea of center of mass. What we're going to say is, let's imagine that we've got some kind of a system with a mass and a board of some sort. And instead of just saying, hey, what's going to happen if we put our fulcrum at the center or wherever we're going to put it, will it tip left or right? Instead, what if we ask ourselves, where should we put the fulcrum in order to have our system be in perfect balance? That point, which we call x bar, is called the center of mass. It's where the fulcrum goes to get the system to balance. Well, if the system balances, the moment must be 0, right? The moment can't be negative or positive. It can't tip either left or right. The moment must be 0. So here are a couple of simple examples that use this idea. First of all, suppose we have two children playing on what we'll call a fair seesaw. In other words, the center of mass, or the fulcrum rather, is right at the center. First child's mass is 25 kilograms over here on the left, and she sits 1.8 meters from the center. Notice I've called that a negative 1.8 because it's to the left of the center. Second child's mass is 32 kilograms, and he's going to sit to the right. I'm just calling his distance x because I don't know where he's going to sit. I would like to find out how far from the center should he sit in order for that seesaw to balance. So I'll use the idea that in order for the seesaw to balance, the moment has to be 0. Here's the moment for the girl. Mass of 25 times a distance, negative 1.8, plus the moment for the boy. Mass of 32 times distance of x. And that's got to sum up to a moment of 0. Did my little algebra here. And it turns out that the boy needs to sit 1.4 meters from the center. Notice because he's heavier, his distance from the center, or the fulcrum, is less than hers. All right, in the next example, we're going to figure out where to put the fulcrum. We'd like to build a seesaw again for two children. Same two it looks like because the girl is still 25 kilograms and the boy is still 32. So here they are sitting on the two ends. We have a 16-foot board to make the seesaw. So I called one end x equals 0 and I called the other end x equals 16. And the children are sitting at the far ends. Where should we place this fulcrum? So I'm just saying, where's the C value such that this is going to balance perfectly? Okay. So here we go. Here's my moment equation. Here's the girl. 25 is the mass times her distance, 0 minus C, plus here's the boy, 32 kilograms, times his distance, 16 minus C. And the sum of the moments has to be 0 if we want the system to balance. Again, just a bit of algebra there, and I turned out that C was just about 8.98 feet. So, about 9 feet. And again, notice it makes sense, right? It's going to be further away from the girl because she's lighter. We have to put it closer to the boy so that his distance is decreased and their moments will balance out. All right. Caught up with myself here. In the example above, suppose that we actually wanted to have 4 children playing on the seesaw. So in addition to the 2 children that we already have here, we're going to have 2 extras. The girl joined by her identical twin sitting a foot in front of her, and the boy by a friend with a mass of 30 sitting 2 feet in front of him. Now where do we place our fulcrum? So we have the same 16-foot board. And I'm going to start with the same 2 children we had. 25 kilograms here, 32 kilograms there. The girl has an identical twin who's sitting 1 foot in front of her. So this would be x equal 1. And if she's truly identical, I'm thinking 25 kilograms for her as well. The boy's friend has a mass of 30. And he sits 2 feet in front of the boy, so that's going to be 14. And same question. Where should we put our fulcrum in order for that system to balance perfectly? So same idea, we just have 4 terms this time. Okay. So starting from the left, 25 times 0 minus C, plus 25 times 1 minus C, plus 30 times 14 minus C, plus 32 times 16 minus C, has to equal 0. Bunch of algebra. When you combine them all, you get 957 minus 112c equals 0, and that gave me a C of 8.54. So that's where we'd put our fulcrum this time. Right. That then, in these two cases, is actually the location of what we call the center of mass. And because of that, we sometimes write it using the notation x bar equals 8.54. It's the one place that you can support the system so that it will be in perfect balance. All right, I'd like to generalize this idea now to having infinitely many weights, perhaps even thinking about them as just the little tiny pieces of the board itself. So we'll start with the idea of, now what if we have n objects? If I wanted to balance, oh, I'm sorry, I want to do that differently. I have a blank for us this time. Got ahead of myself. All right, so I'm going to assume now that I have n objects placed along my board. I want my moment to be 0, and I'd like to find C, also known as x bar, the center of mass. What I'm going to do, instead of trying to draw it, I'm just going to generalize from what we've done here. In every case, we took the mass times the location minus C, or x bar. And we just added all of those up, right, until we got 0 for the total moment. So if I use that same idea, I could say I'd have my first mass, m1, times its distance from the center, x1 minus c, plus I'd have my second mass, times its distance from the center, x2 minus c, and so on and so forth, until I get to my last, or nth, mass, times its distance from the center. And I want the sum of all of those little moments to be 0. I'm going to go ahead and just do a little bit of algebra here. I'm going to distribute, so I'd have m1 x1 minus c m1 and so on. And I'm going to gather all of the x terms together and then all of the c terms together. So let's see, if I look at all of the terms with x's in them, and if I factor out, actually I can't really factor out, sorry, let me just write it as a sum instead. I would have the sum of m times x for each one, so mi xi, as I goes from 1 to n. And then I'd have minus, all of the rest of these terms all contain a c. This is where I want to factor. So I'm going to factor the c out of the rest of these. And then I'd have the sum of m1, m2, all the way through mn. So the sum of all the mi's, as, I goes from 1 to n again, must equal 0. Notice I factored out the negative, which is why I could sum the m1 plus m2 plus ... plus mn. So I would have the sum, as I goes from 1 to n, of mixi equals c times the sum, as I goes from 1 to n, of mi. And again, remember my goal is to find c. That's my center of mass. So if I just divide, I got c. And look at what I really have here. That's the sum of mass times distance. That's moment, divided by the sum of the masses. That's really mass. Right? But here's really the formula that I'm looking for. All right, what if I extend this to infinitely many objects? So instead of having n objects, I now have infinitely many objects. Well, we've seen this so many times, we don't have to draw it all out for ourselves, right? We'd essentially be taking the limit of this as n goes to infinity, which is going to give us c is equal to, the limit of a sum is always an integral. So it would be the integral of the mass times x dx over the integral of the mass dx. And then we'll remind ourselves that the integral, if the mass is actually given to us as a density function, this could be rho of x times x dx. And this could just be rho of x dx. So mass is really rho dx. Mass again here is rho dx. And we often just write this as the integral from a to b of rho of x times x dx, over the integral from a to b of rho of x dx. And we call it x bar, our center of mass. And this is combining some things that we had before, right? Replacing the mass with the integral of rho dx, like we did earlier in this section. All right, lastly, let's just go ahead and use those formulas to do an example or two. So I want the mass and then the center of mass for each thin bar. So in A, there's my density function for a bar that runs from 0 to pi. Mass would be the integral from 0 to pi of the density function, 2 plus cosine x dx. Okay. Again, you're welcome to do that on the calculator if you want to. This one actually just comes out to 2 pi. To get the center of mass, I'm going to take the integral from 0 to pi of that same density function, 2 plus cosine x, times another x dx, over the integral from 0 to pi of 2 plus cosine x dx. Okay, notice I'm just using this formula now, right? Density times x dx, and then just the density dx is all I'm doing. Okay. Top integral came out to about 7.87. The bottom is actually this one, it's 2 pi. And so that turns out to be a 1.25. So the center of mass here is 1.25 from the left-hand end. The mass of the bar is 2 pi in whatever mass units we happen to be using. Let's try one more. In part B, we have a density function that's a piecewise function. So notice that to get the mass this time, again, I'm just integrating the density function, but I'm going to have to do it in two pieces. From 0 to 1, my density function is x squared. And from 1 to 2, my density function is x times 2 minus x. First integral comes out to a third. Second integral comes out to 2/3. So I just get a mass of 1. The center of mass. Still going to have to go in 2 pieces. So on the, 0 to 1, I would have my density function x squared times that extra distance x dx plus from 1 to 2 my density function x times 2 minus x times the extra x for distance dx, right? I'm just doing this. Density times x for each one of those. The denominator is the mass, which we've already calculated. That was just 1, so I'm just going to steal that answer and put it right there. And if you do all of this, that whole numerator comes out to 7/6 divided by 1 gives us 7/6 for our center of mass. And that brings us to the end of our discussion of Part A of 6.7.